It's amazing when you really think about it. Everything we see around us, like everything. This table, these microphones, even us, you and me, is made from the same tiny building blocks: protons, neutrons, and electrons.
Yeah, it really is.
And it doesn't stop there. We look out into space at planets, stars, even entire galaxies, and as far as we can tell, it's the same recipe everywhere. You've got these three basic ingredients, and they're just arranged in countless ways.
Countless ways, exactly.
But there's a big mystery here. You see, for decades, scientists have been searching for something else, something like a mirror image of all this familiar matter. We call it antimatter.
And it's a really fundamental question. Why is the universe so chock full of matter like us? But we haven't seen much of this antimatter counterpart. Early on, physics seemed to suggest a beautiful symmetry, almost like the universe should have been made with equal parts of matter and antimatter.
It's a real head-scratcher. So for this deep dive, we're going on a journey into the world of antimatter. We'll explore what it is, some of its weirder characteristics, and the groundbreaking research going on at places like CERN, all in an effort to unpack this cosmic imbalance. And just to be clear, we're not talking about some science fiction fantasy here.
No, not at all.
Antimatter is real. It's a solid part of our best understanding of physics, something we've known about for almost a century now.
That's right. The story really takes off in 1932. Carl Anderson was working at Caltech using something called a cloud chamber.
Oh, the cloud chamber, classic.
He was studying cosmic rays, these incredibly energetic particles that are constantly bombarding Earth from space. See, in a cloud chamber, charged particles leave a trail, and when you put a magnet around it, they curve.
Right, like the little bar magnets we used to play with.
Exactly. The direction of that curve tells you if it's a positive or negative charge, and how much it curves tells you how massive the particle is. So Anderson saw particles curving one way, electrons negatively charged, no surprise there. But then he saw something strange. These other particles, positively charged, but way too light to be protons. In fact, they had the same mass as electrons, but with a positive charge.
Whoa, like finding a mirror image, a plus instead of a minus.
Exactly. That's how we first detected antimatter, those anti-electrons we now call positrons. A monumental discovery, and he absolutely deserved the Nobel Prize he got for it in '36.
Definitely a Nobel-worthy discovery. But here's the kicker. These positrons weren't a complete surprise, were they?
You're right. A few years before, around 1928, Paul Dirac, this brilliant physicist, had actually predicted them. He was working on a way to describe electrons using both quantum mechanics and Einstein's theory of special relativity. A tough problem.
Trying to mesh those two giants.
Yeah. And when he did, his math showed something wild. There couldn't just be one type of electron. The equations only worked if there were two. One with a negative charge, that's our everyday electron, and another with a positive charge, the positron.
The math forced the positron into existence.
Pretty much. This mathematical object he found, called the Dirac spinor, basically said, hey, there should be a twin particle for every electron, but with the opposite charge. He predicted antimatter before anyone had ever seen it. Amazing, right?
It really is, and it gets even crazier. This twin particle idea, this isn't just about electrons.
Absolutely not.
There's an antimatter twin for every type of particle.
Exactly. For every single one. You've got quarks, which make up protons and neutrons. Well, they're antiquarks too. They team up to make antiprotons and antineutrons. And you can go even further. These antimatter building blocks can actually combine to form whole antiatoms, even antimolecules.
Okay, mind blown. So in theory, you could have an entire planet, a star, maybe even a galaxy, all made of antimatter. And if you saw it through a telescope, you wouldn't be able to tell it was antimatter just from looking.
Nope, not at all. An antimatter planet, if we could observe one from afar, would look, behave, and even interact gravitationally, just like any other planet we see.
Whoa. It just really drives home this big question, this fundamental asymmetry. If matter and antimatter are so similar, why is the universe we see basically just matter?
That's the million-dollar question, isn't it?
This imbalance, which scientists call the baryonic asymmetry of the universe, has been a driving force behind research for a long time. And that's where places like CERN come in. With their huge particle accelerators, they're able to create, trap, and study antimatter in ways we never could before.
Yeah, those guys are pushing the boundaries of what we know.
So we know it exists, but what makes antimatter tick? How does it behave compared to the regular stuff?
Well, we've studied isolated antiparticles, and their fundamental properties, like their mass, are identical to their matter partners. A positron weighs the same as an electron, An antiproton, the same as a proton, it's a perfect mirror image as far as mass is concerned.
But what about their behavior? How they interact with the forces of nature?
Let's start with electromagnetism. That's the force responsible for, well, electricity and magnetism and how charged particles interact.
The one we're most familiar with in our daily lives.
Exactly. Experiments show antiparticles act exactly like the theory predicts, just with the opposite charge. Remember Anderson's cloud chamber. Positrons curving the opposite way to electrons. That's the opposite charge in action.
Right. But there are other forces at play too, right? Gravity, the weak nuclear force, the strong nuclear force. Is it there where things get a bit less symmetrical?
You're getting to the heart of it. Things get really interesting when we look at the weak nuclear force. Back in the 50s and 60s, physicists found some surprising differences in how it treats particles and antiparticles. The first one had to do with a property called handedness, or chirality.
Handedness. I know my right hand from my left, but for tiny particles.
Yeah, it's a bit abstract. Think of it like this. Ordinary particles, the matter kind, only feel the weak force if they have a specific orientation, like a left-handed spin, if you will. And antiparticles only interact if they're right-handed.
So it's like the weak force is a bit picky.
Yeah, you could say that. It only shakes hands with certain particles, depending on their handedness.
That's wild. But it gets even weirder, right? It's not just that it interacts, but the strength of the interaction is different too.
You got it. The second, even more surprising finding was that this difference in handedness also meant a difference in the strength of the weak force. Right-handed antiparticles don't just interact differently with the weak force, they actually experience a different strength of this interaction compared to left-handed ordinary particles.
Whoa. Okay. So what does this all mean in the grand scheme of things? What are the real-world consequences of this difference in strength?
Well, one way this plays out is in radioactive decay. That's a process governed by the weak force. Because of this difference in strength, the chances of a nucleus decaying radioactively are slightly different for regular matter compared to antimatter.
So the mirror isn't perfectly reflecting here.
Exactly. This subtle but crucial asymmetry was first observed back in 1963 by James Cronin and Val Fitch, and actually won them a Nobel Prize.
Another Nobel-worthy discovery. So I imagine when this asymmetry was first discovered, there was a lot of excitement. This difference in the weak force, was it seen as a potential answer to this matter-antimatter imbalance?
That was definitely the hope. You know, maybe the weak force had this slight bias towards creating matter over antimatter in the early universe.
The weak force nudged the scales.
Maybe, but the math didn't quite add up. Turns out this difference, while important, wasn't big enough to explain the huge amount of matter we see and the lack of antimatter. It's like finding a tiny crack in the mirror, but not the huge shatter that would explain everything. So, great discovery, Nobel Prize earned, but the ultimate mystery remained.
Okay, so the weak force isn't the whole story. What about the strong force? That's the one that binds protons and neutrons together in the nucleus. Super strong, as the name suggests.
You would think, following the pattern with the weak force, that there might be some difference in how left-handed particles and right-handed antiparticles feel the strong force, right?
Hey. Yeah, seems logical.
Well, once again, antimatter threw us a curveball. Every experiment, and I mean every single one, shows the strong force doesn't care if it's dealing with matter or antimatter. It treats them exactly the same. No asymmetry, no difference in strength, nothing.
So the strong force is totally blind to this matter-antimatter difference.
Blind as a bat.
Which brings us to gravity, that final fundamental force. And this is where things are getting really interesting at CERN. They're trying to nail down, once and for all, if gravity acts differently on matter and antimatter.
Absolutely. It's a really exciting area of research.
But it sounds like most physicists are betting it won't, right?
That's the common assumption. Think back to Galileo dropping objects from the Leaning Tower of Pisa, or Newton's law of universal gravitation. The key takeaway is that gravity doesn't care what something's made of, just how much mass it has. A cannonball and a feather, in a vacuum, will fall at the same rate.
Right, a classic physics demo.
And this is a cornerstone of Einstein's theory of general relativity, his equivalence principle. It says that the mass that determines how much something resists being pushed, its inertia, and the mass that makes it feel gravity are the same thing. So, in a gravitational field, everything falls at the same rate, no matter what it's made of.
So, given this well-established principle, why bother trying to measure gravity's effect on antimatter? It seems like a huge undertaking for something we think we already know the answer to.
Well, there are a couple of good reasons. First, there's that mystery of the baryonic asymmetry, the matter-antimatter imbalance. We have to explore all avenues, even the unlikely ones.
Leave no stone unturned.
Exactly. The second reason is a bit more speculative. Some theories trying to explain dark matter and dark energy, two big cosmic mysteries, suggest that antimatter might actually have a negative gravitational charge.
Negative gravitational charge, meaning it would fall up. Wouldn't that be a sight to see?
It would defy our everyday experience for sure. So, to test this, a few very sophisticated experiments are running at CERN: Aegis, GBAR, and LFA. In fact, the LFA team recently published some big findings in the journal Nature, giving us actual data on how antimatter accelerates under Earth's gravity. After decades of assumptions, we finally have hard evidence to work with.
It must have been a huge moment finally getting some concrete data after all this time. But how did they manage to measure something so incredibly subtle? It sounds impossibly difficult.
Oh, it was a phenomenal feat. It started with generating a beam of positrons, remember those anti-electrons, from a radioactive form of sodium, sodium-22. Now, when positrons meet normal matter, they usually annihilate each other in a burst of energy.
Oh, gone.
Exactly. But a tiny fraction of these positrons actually survive, and the researchers managed to capture those survivors, cool them down to ridiculously low temperatures, and then trap them using carefully arranged electric and magnetic fields.
But you said earlier that measuring gravity's effect on individual positrons is almost impossible, right? They're just too light, and even the tiniest electromagnetic fields could mess everything up.
You're absolutely right. So they needed a trick, and it was a brilliant one. They took those trapped positrons and combined them with antiprotons to make neutral antihydrogen atoms. Antiprotons are made by smashing high-energy protons into a metal target. And since these new antihydrogen atoms are neutral, meaning no net electric charge, they're way less affected by stray electromagnetic fields, making them ideal for gravity experiments.
Like trying to measure the fall of a feather in a hurricane, but now you've somehow managed to shield the feather from the wind.
That's a great analogy. So now they have these antihydrogen atoms, the neutral ones, but how do they isolate them and actually measure the effect of gravity?
Yeah, especially since gravity is such a weak force compared to the other ones.
Well, they use a special chamber with a near-perfect vacuum to minimize unwanted interactions. Inside, the antihydrogen atoms are trapped using a complex arrangement of magnetic fields, sort of like a magnetic bottle. Then, they carefully, and I mean very carefully, weaken the vertical magnetic fields that are holding those antihydrogen atoms.
What does that do?
Well, because those atoms are always jiggling around due to their thermal energy, this weakening of the field allows them to slowly escape, either from the top or the bottom of the chamber over about 20 seconds.
I see. So it's like tilting that magnetic bottle ever so slightly, allowing them to dribble out one by one.
Exactly. Now here's the crucial part. When one of these escaping antihydrogen atoms hits the wall of the chamber, which is made of regular matter, they annihilate, releasing a burst of light.
Ah, that poof again.
Yep, but a very useful poof. By carefully counting the number of annihilation events happening at the top versus the bottom of the chamber, they can figure out which way gravity is pulling those antihydrogen atoms.
Okay, so if gravity is pulling antimatter down, like normal matter, they should see more annihilations at the bottom of the chamber.
You got it. To make sure they were interpreting things correctly, they ran simulations. These simulations showed that if antihydrogen experiences normal gravity, they'd expect about 85% of the annihilations to happen at the bottom. If antimatter was falling upwards, only 20% would be at the bottom. And if gravity had no effect at all, it would be about 50-50, with some slight variation due to imperfections in the experiment.
Drumroll, please. What did they actually see?
The results were pretty clear. Roughly 75% of the antihydrogen atoms that escaped ended up annihilating at the bottom of the chamber. That strongly points to normal downward gravity for antimatter, just like we'd expect for regular stuff.
Okay, that seems pretty convincing. But I imagine they didn't just stop there, did they?
Oh, no. To double-check and eliminate any potential biases in their setup, they did the experiment multiple times, each time adding a small, controlled magnetic force, either pushing the antihydrogen atoms up or down to simulate different gravity conditions.
So like adding a little extra push or pull?
Exactly. Then, they compared the results from these different runs to their simulations for various gravity scenarios. The best match, the one that fit the data the closest, was for downward gravity, acting just like it does on regular matter.
But you said their best estimate for the gravitational acceleration was slightly lower than the usual 9.8 meters per second squared we're used to, right?
Yes, it came out to about 0.75 g, but here's the important thing. Their measurements had uncertainties. which are super important in any experiment. You always need to know how precise your result is.
The infamous error bars.
Right. After accounting for everything, their best estimate, with error bars included, was 0.75 G plus or minus 0.13 G due to potential systematic errors and plus or minus 0.16 G from random statistical fluctuations. This means a full 1 G acceleration is still comfortably within their margin of error, completely compatible with their findings.
So while future experiments might refine this measurement, it's safe to say this groundbreaking work effectively rules out those more outlandish ideas of antimatter falling up.
Pretty much. It seems antimatter, while strange and exotic, still obeys the same gravitational rules as the rest of us.
So, to summarize, we know antimatter is real. It has the same mass but opposite charge as its matter counterparts. Its electromagnetic interactions are as expected, but the weak force treats it a bit differently, though not enough to explain the matter dominance of the universe. And now it seems gravity plays by the same rules for both matter and antimatter. But that still leaves the big question unanswered. Why are we here in a universe made almost entirely of matter?
It's a puzzle that continues to baffle physicists. If the laws of physics, as far as we can tell, are mostly symmetrical for matter and antimatter, then the overwhelming presence of matter in the universe is a huge mystery. It suggests we might be missing something fundamental in our understanding of physics, or perhaps the very beginning of the universe, the Big Bang itself, started with an imbalance baked right in.
A huge imbalance playing out over billions of years. It's a lot to wrap your head around.
It is, but that's the beauty of science. It's a never-ending quest to understand the universe and our place in it.
Well said. A big thanks to you for diving into the fascinating world of antimatter with me. And to you, dear listener, I'll leave you with this. We've learned that antimatter, despite its weirdness, doesn't float away due to anti-gravity. It seems gravity keeps everything grounded, even the exotic stuff. But it's this very similarity that deepens the mystery. If matter and antimatter are so alike in so many ways, then what tipped the scales in the early universe? What made matter win out? What made our existence possible? It's a cosmic riddle, and maybe, just maybe, you'll be the one to help solve it.
It would be quite a feat to unlock that mystery.
Keep those brains buzzing, folks, and until next time, happy